Hello everyone, my name is Christian Harris, and today I'm going to be presenting the paper titled Target Tracking in the Presence of Intermittent Measurements by Network of Mobile Cameras. My co-authors are Dr. Zachary Bell, Mr. Roonhan Sun, Dr. Emily Doucette, Dr. Will Curtis, and Dr. Warren Dixon. Traditionally, the problem of tracking a target subject to intermittent feedback has been addressed using probabilistic estimators. Here we have two examples, on the left the common filter-based approaches, and on the right particle filters. These approaches utilize an update and predictor schema to retain pose estimates of the target when feedback is not available, and typically require knowledge of the probabilistic density or mass functions for the uncertainties in the system. Some of their disadvantages are they often linearize the target's nonlinear dynamics, result in local convergence of the mean estimate, and optimal estimation is achieved when the limit of sample points approach infinity. More recent tracking solutions offer a deterministic approach to the intermittent feedback problem. In this paper by Nuparik and others, an update and predictor schema is used like in the traditional tracking solutions. However, the nonlinearities in the system are exploited for estimation, assumptions are made about the boundedness of uncertainties in the system, and the approach yields uniformly ultimately bounded results for the estimates. However, the switch systems analysis provided in this paper is not suitable for camera networks. Specifically, an average dwell time condition is offered which states, for a given number of cycles of losing and regaining feedback, the average time spent in the stable regions is sufficient for guaranteeing a UUB result provided that the condition is met. However, if the target's positional uncertainty grows larger than the field of view of a neighboring camera in the network, regaining feedback cannot be guaranteed using the proposed approach. In our previous work, we extended the previous deterministic result to a network of stationary cameras, developed new minimum and maximum dwell time conditions, and a network configuration criteria to guarantee the estimator and predictor stability. The image on the top right illustrates our approach where the target is traversing the tracking environment from left to right. The target's motion model is approximated when it's within the field of view of the camera network, and then this approximated motion model is used in a predictor for when feedback is not unavailable. This development provides a conservative but stronger dwell time analysis compared to previous results, provides a metric for how long estimates can be trusted after losing visual feedback of the target, and can be used as a tool for designing stationary camera networks to improve tracking performance while reducing the number of cameras needed for the tracking objective. However, the major drawback to this approach is that the entire network needs to observe the target to ensure that the network satisfies the dwell time condition for all feedback cycles, which can be impractical. The objective of this paper was to develop a framework that ensures that the estimator and predictor used for tracking the target remains bounded for all feedback cycles without requiring the entire network to observe the target. To do this, we've allowed the cameras in the network, denoted by script CJ, to move within operating regions denoted by script OJ. The image on the right illustrates a new tracking scenario where the target M traverses the target environment according to an unknown motion model. Additionally, the space outside the operating regions are denoted by OCC, and the target's field of view is denoted by script VJ. Note that feedback is available only when M is contained within VCJ. The task now is to design a controller that regulates the pose of each camera to ensure that the target remains within the field of view of the jth camera when it's traversing the jth operating region. Also, we want to design an estimator and predictor for tracking the target by approximating its motion model. Finally, we want to develop minimum and maximum dwell time conditions to ensure that the tracking objective remains bounded for all cycles of losing and regaining feedback. First, I'd like to start by introducing the kinematic models used in the development of the camera's pose controller, where script CJ identifies a particular camera in the network. The camera's linear velocity, denoted by p dot, is the sum of control input u and an unknown exogenous disturbance d acting along the camera's xyz axes. Similarly, the camera's angular velocity, denoted by q dot, is also defined by the sum of control input and exogenous disturbance about the camera's axes, but then mapped into the quaternion space using the b term. These linear and angular velocities are then stacked to yield the time derivative of the camera's pose with respect to the global frame. Now, the jth camera's pose error system is represented through eta tilde, where eta Cj with respect to the global frame g is the pose of the camera, and eta Cj with respect to g desired represents the camera's desired pose trajectory. Taking the time derivative of this error system yields our closed-loop error system as a function of a control input vector, disturbance vector, and the desired velocity state of the camera. It is assumed that there exists a desired trajectory that's at least C1 continuous that allows the camera to track the target when it's within the jth operating region and allows the camera to loiter when it's not. Now informed by the following stability analysis, a sliding mode controller is designed to regulate the camera's pose. Using the Lyapunov function candidate VJC, the camera's pose error system is proven to converge exponentially given the proposed controller design. Now let's define the kinematic relationship between the target M and the jth camera Cj. Eta dot M Cj stacks the target's linear and angular velocities p dot and q dot respectively with respect to the jth camera. Manipulating the terms in eta dot yields a new expression in terms of eta dot mj highlighted in red and fj. The red term in this expression refers to the target's motion model in the global frame, and this is a term that we wish to approximate. Note that all the terms in eta dot mj are known or measurable when the target's within the field of view of the jth camera. Using this information, a neural network is used to approximate the target's motion model, where wj is an unknown matrix of ideal weights, sigma j is a vector of basis functions, and epsilon j is a function approximation residual. The state estimation error is represented through eta tilde mcj, where eta hat mcj is an estimate of eta mcj, or the pose of the target with respect to the jth camera. Taking the time derivative of eta tilde mcj yields eta tilde dot mcj, and in this form we can introduce the approximated motion model into the analysis, highlighted in red. The behavior of the state estimator is designed through eta hat dot mcj and is known as the state update law. The switching signal sigma fj is used to identify when feedback is available, resulting in case A, or when feedback is unavailable, resulting in case U. When feedback is available, the A case in the state update law drives the behavior of the state estimator. When feedback is unavailable, the U case drives the behavior of the state predictor. Since estimates of the ideal weights are used in the design of the state update law, a separate weight estimator is needed. W tilde j is used to describe the error between the constant ideal weight matrix and the estimated weights. Taking the time derivative of W tilde j yields W tilde dot j, and it's here where the weight update law is introduced. This update law utilizes a complementary concurrent learning approach for estimating the ideal weights of the neural network. This approach functions by using past pose and velocity state data, highlighted in green, to improve the rate of convergence of the estimator, where this rate is dependent on the data's excitation or richness. Like the state update law, the weight update law depends on the availability of state feedback, where the A case will be used in the state estimator, and the U case will be used in the state predictor. The following Lyapunov function candidate Vmj is used to analyze the behavior of the error systems for this problem. Taking the derivative of the Lyapunov function yields v.mj, where the expression is a function of the closed-loop error systems eta tilde dot mcj and w tilde dot j from the previous slide. The proposed state and weight update laws use the following stability results, highlighted in red, blue, and green, where a new switching signal is introduced. Recall that depending on the richness of the pose and velocity state data in the history stack, the state estimates converge at different rates. Sigma dj identifies whether the history stack has met the excitation condition, occurring at time capital Tj. For the blue result, feedback is available and the excitation condition is not met, resulting in exponential convergence to the positive constant beta 1. For the green result, feedback is available and the excitation condition is met, resulting in exponential convergence to a positive constant CUB, where CUB is less than beta 1 and the convergence rate is faster. And for the red result, feedback is unavailable, resulting in exponential growth of the error systems. To ensure that the error systems do not grow unboundedly, a maximum dwell time condition is developed. Consider a scenario where a camera is tracking a target in the jth operating region. At time t off nj, the target leaves the operating region and enters OCC, where feedback is unavailable. The goal is to determine how long the target may remain in OCC, denoted by delta t off nj, without causing the error systems to grow past V upper bar. V upper bar represents the upper bound on how much propagation error can be tolerated. For this application, we don't want the positional uncertainty of the mobile robot growing larger than the field of view of the neighboring camera in the adjacent operating region. Theorem 1 states that, for the jth operating region, the proposed estimator and predictor remain bounded for a cycle of having and losing feedback, provided that the following dwell time conditions are met. Here, a new switching signal is introduced, identifying whether the excitation condition for the history stack was met in a previous feedback cycle. To better visualize the effect of the new switching signal, let's first consider the case where the excitation condition on the history stack has not been met. The evolution of the air systems are illustrated on the right where, when feedback is available, the air systems are bounded by the blue trajectory. Then, when feedback is unavailable, the air systems are bounded by the red trajectory before reaching V upper bar. For the second case, the excitation condition has been met but during the current feedback cycle, occurring at time capital Tj. This results in the air systems being bounded by the blue and green trajectories when feedback is available. Additionally, since the air systems exponentially decay to CUB instead of beta 1 like in the previous slide, delta T off Nj will increase, allowing the target to spend more time in the unstable region before exceeding V upper bar. Finally, for the third case, the excitation condition has been met but during a previous feedback cycle for the operating region. This results in the air systems being bounded by the green trajectory for when feedback is available. A minimum dwell time condition is also developed to ensure that the air systems decay below a specific threshold, in this case V underbar, before the target leaves the operating region. This is particularly important because the amount of time V can grow before becoming larger than V upper bar in the unstable region is dependent on the convergence of the air systems when feedback was available. Theorem 2 states that, after the maximum dwell time condition has been satisfied, and a target has entered the field of view of the neighboring camera, a new feedback cycle begins for the adjacent operating region, and the estimator and predictor will be bounded by V underbar during the stable region, provided that the following minimum dwell time conditions are met. In conclusion, a controller, estimator, and predictor was developed for tracking a target using a network of mobile cameras. Minimum and maximum dwell time conditions were also developed, ensuring that the target tracking objective remains bounded for all feedback cycles in operating regions, provided that the dwell time conditions are met. Some of the work's implications are, it can potentially reduce the quantity of cameras needed for a tracking objective, or it can increase the coverage area of the network. Future work will seek to validate the performance of the tracking solution through experimentation. Also, we would like to investigate additional ways to increase the time the target may remain in the unstable regions. Thank you for taking the time to view this presentation, and I hope you enjoyed the work. If you have any questions, please address them to charris319@ufl.edu. Thank you.